Good morning, good afternoon, or good evening, according to your time zone. My name is Vivian Lutz, and I'm pleased to welcome you to this online training series, Observing Marine Ecosystem Structure and Function from Microbial Communities to Fisheries and Human Health. This is a virtual component of the in-person training that is going to take place in India, preceding the TREVOR Symposium. But of course, apart from the students that are going to go to India, this is open to the whole marine research community, and especially encouraging early students and early career professionals. And we're very pleased to see a very large audience today. So that's great. This is a very good beginning. Also to remind you that this is a lecture, so please take advantage of the knowledge of our speaker today, as well as the panel that is contributing to the discussion, and ask all the questions that you want, and post them in the Q&A box, and we will get to them at the end of the talk. So today's speaker is Dr. Lorin Biermann from UMETSAT, Germany. And we also have a panel composed of Dr. Ben Loveday, also from UMETSAT. And he's lead of the Copernicus Marine Training Service. And we have Dr. Likat Krug, scientific coordinator of POGO from Portugal, and Dr. Shubhasa Siendranath from a senior scientist from PML UK. So our speaker, Dr. Biermann, she has recently joined the climate services team at UMETSAT, where she's working at the interface of satellite Earth observation, machine learning, and user engagement. Her background is a marine remote sensing education, and she's now applying those skills to better understand data challenges within ML-driven meteorological services and climate research. Lorin is also supporting the development of tools and services that enable Earth observation and machine learning applications, including collaborative labeling for Earth system feature detection. And she's going to talk today about observations using satellites. So, Lorin, the floor is yours.
Thank you so much. Yes, let me share my screen and get going. There we go. Okay. Thank you so much for that lovely introduction. Is everything fine? You can hear me and see my screen, just to confirm. Great. Okay. So I just want to say how lucky I am to be here today and how grateful I am. I've been given the stage to talk about basically the thing that makes me happy, the thing that makes my world go round, which is observations of our Earth using satellites. And in order to try and fit all of my enthusiasm into just 1 hour, it's going to be the biggest challenge for me today, because I absolutely love what I do. I love satellites and I love spying on our Earth from space. So I thought the best way to try and squash everything I love into 1 hour is to chunk what I plan to talk to you about today into 4 sort of broad sections. The first thing is I'm going to talk to you a little bit about UMETSAT. So not just because that's where I work, but because I suspect in the next few weeks you'll be using a fair amount of our data. And so I thought it might be useful to introduce you to who we are and the satellites that we are operating for data delivery for your applications. I'm also then going to take you a little bit possibly back to your high school, where you learned about the electromagnetic spectrum, but it is not to punish you. It is in fact just to show you how we leverage different parts of the spectrum to learn different things about our Earth using different types of sensors. And I think it's really cool. And then my favorite part of today is a new thing that I've done, which is I've gone back as far as possible to find out where remote sensing by satellites actually started, so that we can better appreciate how lucky we are to be here right now today with freely available global satellite data at our fingertips, all different types from all different types of places, able to do something like that where maybe 40, 50 years ago that wasn't even possible. So within generational memory. And then finally, because of course, this is a very important lecture series that has a focus on marine ecosystem structure and function, I am going to do a very brief overview of marine remote sensing as a foundation. So we're all on the same page and you guys are all ready to learn from the other specialists over the next few weeks. So let's start with learning about EUMETSAT and our fleet of satellites. So what does EUMETSAT actually stand for? It stands for the European Organization for the Exploitation of Meteorological Satellites. And that's a very big mouthful, but the thing that I like about EUMETSAT, and I think the thing that you really need to remember, is that it's an operational organization that is there to serve the needs of the many. And it's our job to ensure that the data that is needed for timely and accurate weather and climate research and services is made available primarily to member states. So 30 member states, there are their flags. They're the ones that are our bosses because they pay our bills. But we also have very, very good collaborative agreements with India, as well as China, Japan, Korea, Canada, and the USA. And we have lots of user agreements as well with, for example, all the countries in Africa. So it's not just that we serve the member states, it is also that it is our priority to ensure that everyone in the world has access to really important satellite data for their weather and climate services and research. And we do that globally using 12 satellites that we currently operate. Now, the bread and butter of EUMETSAT is weather, so the meteorological function is our primary goal. However, this sort of big core part of EUMETSAT might not be of immediate interest to you guys. So I'm not going to talk too much about the satellites that we have there. I will mention them in a little bit, but I will sort of rather highlight the satellites that we are operating as part of our optional and third-party programs. And this is where the marine focus comes in. So we are operating satellites like Sentinel-6, for example, that is collecting very high precision measurements of the ocean and sea surface height in particular, or ocean altimetry. And we are doing this as part of mission continuity to ensure there is an uninterrupted time series of sea surface height on global scales. We also participate in the Copernicus program. So that is our third-party program. And I suspect that there's going to be quite a lot involving Sentinel-3 over the next few weeks. So I will give special mention to Sentinel-3, which carries the ocean and land color instrument, SLSTR for temperature, and STRAL again for sea surface height. So there's two that are collecting data on sea surface height. And I suspect we'll be talking about Sentinel-3 quite a lot, but it's also worth mentioning that Sentinel-4 and 5 are part of the third-party program under the Copernicus program, but these are more atmospheric components. So if you have an interest in global atmosphere, so whether it's pollutants or volcanoes or anything that might be affecting your work and your project from an atmosphere perspective, do know that we are also operating Sentinel-4 and 5. Okay, now I'm going to go out on a limb and I'm going to bet that when it comes to talking about satellites, almost everyone here is very, very familiar with LEO. So the satellites that are polar orbiting in low Earth orbit. And feel free to add to the comments and let me know if I'm right or wrong, because my suspicion is that most of you, if not all of you, are much more familiar and comfortable with satellite data from low Earth orbit than you are from anything else. So I'll quickly tell you about our LEO fleet. We have the METOP satellites that are collecting weather data. They're in sun-synchronous orbit, which already gives you a clue about what the primary sensors are doing. They're probably passive sensors. They're in low Earth orbit and they're sun-synchronous so that they can collect reflected sunlight from the Earth passively. And then, of course, we have Sentinel-3A and B that are doing the same thing. They're polar orbiting. They're collecting data on a daily basis. So they're going around the Earth and they're doing a polar orbiting, the polar orbit, and the Earth is turning underneath them, and they go round and round and round to try and cover all of the Earth at least once a day. Sentinel-3 does that by operating as a constellation, but it does allow us to get revisit times, and we do get data once a day at relatively high spatial resolution, and the instrument aboard Sentinel-3, which is the optical sensor, is ALCHI, where we get our ocean color data from, for example, and that relies on reflected sunlight. It's a passive instrument. And I know I'm throwing these terms around. I know a lot of you know what they mean, but for those of you who don't worry, I will go into a bit of detail in a minute. And then we have our active sensors. They are not in a synchronous orbit with the sun because they don't need reflected light. They are sending out a signal to Earth, and they're reading back what bounces back in order to get very high precision altimetry data. So these are our polar orbiting satellites in low Earth orbit. And I'm really looking forward to looking at the comments later to find out how many of you are aware of the geostationary satellites that we operate, because these satellites operate very differently to the polar orbiters. As the Earth spins, they spin with the Earth. So they actually see the same face of the Earth all of the time. So they move around with the Earth and they're always looking at the same spot. And we have quite a few that are looking over Africa, the Atlantic Ocean, and Europe. And then we have a dedicated mission as well, looking at India and the Indian Ocean. So that is the IODC geostationary satellite, and it is a dedicated mission looking over the Indian Ocean. So these satellites are quite different. But why? Why are there different types of satellites and sensors? Why do we have some in low Earth orbit and some further away in geostationary orbit? Well, the further away part is actually really impressive. And this isn't really relevant, but I think it's really cool, so I'm going to share it with you. We get our low Earth orbit data, and these satellites are sitting at anywhere between 650 and 800 kilometers away. The geostationary satellites are 36,000 kilometers away. And they're not giving us daily data. They're giving us data every 10 minutes, sometimes every 30 minutes, but some of the more modern third generation sensors are giving us data of that section of the Earth that they're looking at every 10 minutes from 36,000 kilometers away at 500-meter resolution, which is just mind-blowing to me. I just think it's incredible that we can do that in this day and age. But to give you an idea of what 36,000 means, if there are any runners in the room or people who are very good at walking and getting their steps in order for you to reach the geostationary ring, you would need to walk 10 kilometers every single day for 10 years. And then you would be able to get to the geostationary ring. So it's really, really far away. So it's amazing that we can see the Earth from so far. The other thing that's different is that the low Earth orbit satellites, as much as they're collecting data every day, they benefit from being able to carry both active and passive sensors. So they're sensors that are, well, I'll talk about this in a little bit more detail, but they're able to get a little bit more by being really close to Earth, whereas the geostationary satellites are only able to carry passive sensors. So that's another thing that makes them different. But despite these differences, they're all united by the electromagnetic spectrum, because all satellite-based Earth observation has to use sections of the electromagnetic spectrum. And by leveraging different regions of it, we can learn different things about our Earth. So, for example, optical remote sensing sits within the visible to the near infrared and shortwave infrared of the electromagnetic spectrum. It's a small section, but that's where we get our optical data. And these are passive sensors that are reading the sunlight that has traveled through space, through our atmosphere. It's gone through to the Earth's surface. It has interacted with the Earth in some way. That reflected sunlight that makes it back out the atmosphere now is able to be read by satellites either hundreds or 36,000 kilometers away from Earth. So again, just incredible that this actually works. And then we have our infrared sensors and our microwave radar that are doing a lot of heavy lifting for measuring the temperature of the Earth. And we can also gain some information about the temperature of the Earth using TV and radio sections of the electromagnetic spectrum. And this is a word that took me a long time to be able to pronounce fluently, radio occultation. And that helps us understand the humidity in the atmosphere, which helps us also understand the temperature. So by leveraging and combining information from different types of sensors at different distances from the Earth, we are able to get a more holistic story about what is happening. Here is an example of Sentinel-3, my favorite satellite carrying the Ocean and Land Color Instrument. This is in low Earth orbit, and it is measuring the reflected sunlight that has traveled back out the atmosphere and is being read by the sensor aboard the satellite. And you can see here that it is collecting data and it's going over a really nice bloom at the moment. It's collecting data over land as well, but what it is unable to do is see through cloud. So you can see that it is seeing the cloud, but it is unable to collect any information from underneath. And so if, for example, we wanted to go back to that bloom, we would have to wait until tomorrow because it's giving us 1 overflight a day. And if that bloom is still there, but it happens to be under cloud, that's just too bad. Unfortunately, there's nothing we can do about it. But if on the 3rd day the bloom is still there and the cloud has moved on, then hopefully we can still continue to monitor that bloom. So this is an example of a passive sensor collecting information about our Earth in low Earth orbit. And these are the sorts of orbits that you get. So it has to go around the Earth every time in order to get the data. And by the end of a full day, the whole Earth will almost be filled with these lines because it goes around and round until it's filled in the Earth. Active sensors in low Earth orbit are different. They send a signal out to the Earth and it reads something back. I always think of this, oh, sorry about that. I don't know what that man is doing. But I like to think of it as a, if I'm walking along the road and I'm bouncing a tennis ball, I'm instinctively understanding how far the ground is from my hand by the speed and distance that it takes for the ball to bounce back into my hand. And if I bounce it on a step, it's going to be much quicker back to my hand. And it's a very simplistic description, but that in a very high precision way is how, for example, this instrument, Poseidon Synthetic Aperture Radar, is collecting information about sea surface height in space and time as it goes over. And the other thing that you might notice between the ocean color instrument that we saw before and this one over here is you can see it's a line rather than a swath. So it's in a long track measurement. And the way that we can understand that better is if you look at about a year's worth of these lines that have been collected by the Sentinel-6 instrument, you'll see that the swaths never really fill themselves in. And in order to actually get a gridded image, like a map view, like we are used to seeing with, for example, ocean color, you would actually have to do interpolation. And it doesn't make it bad. It just means that you have a different type of measurement being made compared to a picture. You have a mathematical, a long track number that you can convert into sea surface height measurements, but it's a slightly different type of measurement. And then, of course, you get the geostationary satellites. And again, just mind-blowing. It's spinning in space and it's collecting the same image of Earth every 10 minutes. So this is what we would call a full disk image collected by a geostationary satellite. And it is doing this, it collects a visible band, it collects water vapor and infrared. So it tells us a lot about the health and temperature of the Earth. But as with the passive sensors in low Earth orbit, it cannot see through cloud, but that's okay for the geostationary ring because for these satellites, seeing the cloud is most of what it wants to do, and it is actually looking for the cloud rather than trying to see under the cloud. But this is the type of data that you get, and this is from the geostationary satellite MTG that is over the Indian Ocean, and you can see it captures a lot of Africa and Europe as well. But this is an image that was taken this morning. It was taken at 9:45, so I went onto UMetView this morning And I went to see what it looked like today. And I can see India's got a lot of cloud today. So it's maybe not a very sunny day, or it certainly wasn't at 9:45 this morning. But this is the point, is that you can see a lot of what's happening with the weather through these satellites. Now, I've just told you about EUMETSAT and how cool our satellites are and how different types of satellites leverage different things in order to look at our Earth. But why is Earth observation from satellite important for marine ecosystem structure and function monitoring? Well, I would say that even if you're looking at something on a local level, it's very likely that something affecting it or something causing change to it might actually be happening at a regional or even a global level. Perhaps it's an El Nino year and that's what's changing things. Perhaps there's a different climate system that's happening, or perhaps there's a huge storm that's moving through that has brought up colder water with nutrients in it and caused an out-of-season phytoplankton bloom. So being able to look at the Earth at different spatial and temporal scales really helps you get a holistic understanding of what might be driving anomalies or changes or shifts in the thing that you're measuring on local to regional scales. So I would say that there's very little else out there that could link together ecosystem structure and function through time and space in the same way that remote sensing from satellite can do. But here we are today, as I said earlier, with global data freely available from different types of satellites and different types of sensors at our fingertips. We are very lucky. And the reason that we know we're very lucky is because we can compare what it was like to try and do this kind of thing in the beginning. And the beginning was not really that long ago. So Sputnik, I would say, is officially the beginning. It's a satellite that was launched by the Soviet Union into low Earth orbit on the 4th of October, 1957, into polar orbit. Now, this might not seem impressive because we're used to satellites, but at the time, no man-made object had been launched into space successfully. And at the time, commercial air travel was still happening on propeller airplanes, and yet they managed to get an instrument into low Earth orbit. Sputnik itself is really lovely. It's a polished metal sphere, no bigger than 58 centimeters in diameter, with 4 external radio antennas that were used to broadcast radio pulses. So all it did was it orbited the Earth and sent out little beeps. And that meant that even very amateur radio enthusiasts could listen to Sputnik as it passed over. And it was traveling at about 8 kilometers per second, and it took about 96 minutes to complete each orbit of Earth. And despite the fact that this was all very experimental and the first time it had ever happened, it managed to do this for 22 days before its batteries ran out. And then on the 26th of October, 1958, it stopped transmitting its radio pulses after 1,440 orbits. So really just quite incredible for the first attempt ever at getting a satellite into space. It burned up on re-entry, and there were a few more Sputniks that were sent out. But despite the fact that all it did was send out radio pulses, satellite scientists still managed to get really valuable information out of Sputnik, scientific information. They were able to see the drag on Sputnik, which gave information about the density of the upper atmosphere, and they were able to get information about the ionosphere as well. What I think is incredible about Sputnik is that this was really the start of the space race. And it was also a key driver for the formation of an organization you've probably never heard of before, called NASA. So the Americans soon followed suit because Sputnik proved that instruments could be sent into space. And the Americans thought, well, if we can do that, wouldn't it be amazing if we could try understand our weather using instruments in space? And TREVOR was a very experimental program. I love this satellite. I've never seen anything more 60s looking in my life. I just think it's so perfect. Those are all of the solar panels to try and improve the longevity of the satellites. It was in different types of polar orbit, but very, very low Earth orbit. And you can actually see on, hopefully you can see my mouse. There is a camera over here. So TREVOR actually stands for television and infrared observation satellite. And the word television might be confusing because for us in this day and age, television is an object that we watch. It's on our walls. But at the time, television actually meant camera. So it's actually a camera over here that they mean by television. And then it also had an experimental infrared sensor to measure, to try and get measurements of the temperature of the Earth. And it was only about 1 meter in diameter and 0.5 meter high. You can see all those solar panels, but it managed to last 78 days after it was launched in 1960 by the Americans. But it still managed to get some pretty cool data. This over here, if you'll give me a minute, is the first, here you see it again, television picture. It's the first camera image, the first photo of Earth from space. And it was taken on April 1st, 1960. It's not the best picture, you know, I would agree with you on that, but still really exciting to be able to take a photo of Earth from space for the first time ever. And as things improved, we started to see more and more interesting things from TREVOR. This was a later TREVOR, and here you can see a hurricane or tropical storm or cyclone that was actually captured for the first time by these satellites. And the other thing about the TREVOR mission is it finally proved that you can take measurements of the Earth from space, and this started the first official Earth observation for weather and climate. And this Nimbus, so Nimbus is a satellite series. Nimbus means rain cloud, so it was specifically to look at weather, but it also paved the way for us to get ocean color data and sea surface height data because we started to be able to get more and more instruments on satellites in space. These satellites, the Nimbus series, were from 1964 to 1978. And for those of you who use Landsat, you'll know that Landsat started a year later as well. So this really did pave the way. But what I'm really excited to show you is Hurricane Gladys over here. This was a system that formed over the Atlantic Ocean in 1964. It was 700 kilometers in diameter. And despite its enormous size, if it hadn't made landfall in Cuba, nobody would have known it was there because it was predominantly happening over the Atlantic Ocean. And without satellites, we wouldn't have been able to see it, know it was there, and then give advanced warning to Cuba that a massive storm was on the way. So this was really important. It's also really important because we know what the temperature of the Earth was back in the 1960s. So it helps us to understand how much things have changed over time because we have very, very good data that go back to the 1960s. And so from about the mid-1970s onward, we couldn't predict the weather without satellite data. It became essential to accurate weather predictions. So for those of you who picked up your phone this morning to check the weather, this is thanks to the Nimbus Foundation, but it also uses the weather satellites that EUMETSAT operates today as well. The accuracy of our weather reports improved so much because we were finally also getting data over the oceans. And I wanted to tell you a little bit about the World Meteorological Organization report that came out in 2022, which showed that thanks to data collected by satellite, the improved accuracy to weather prediction also meant that it caused a decline in global weather-related deaths because we could give better warnings with more advance. So for example, in the 1970s, over 50,000 people per year were dying because they weren't getting accurate and advanced severe weather warnings. By the 2010s, that number has reduced to less than 20,000, even though our weather is becoming more extreme. And I'm really interested in seeing new reports coming out, maybe in 2030, where machine learning has been used to potentially improve and speed up weather predictions even more and potentially save even more lives every year. So we have observations of our Earth from satellite going back to the 1960s, but as you can see, there are big gaps, not necessarily in space, but definitely in time. And as a result, the modern day agencies are really highly invested in mission continuity because gaps are problematic. We want to be sure that we have time series data without gaps so that we can have uninterrupted measurements of the Earth made from space. So in order to get a full time series without gaps, we can go back to the early 1990s. Here's an example of temperature of the Earth going back to the 1990s. This is just air temperature, not sea surface temperature. But in order to harmonize all of the data collected by different satellites, you have to use different approaches to combining sensor data. This is also something that if you are going to be learning about the OCCCI product, a level 3 ocean color product under the Climate Change Initiative, if you're using this product in the next few weeks, or if you used it before, this is another example of where you get data from different sensors and you harmonize in order to get a time series. And I don't know about you, but I can see, this isn't mathematically fitted, but I can definitely see a trend already in the data. And so this is why time series data is so important, is so we can look for trends and anomalies. From the marine perspective, because of course, the series isn't about weather, it's about marine ecosystem structure and function. Those satellites also pave the way for us to get data on sea surface height, sea surface temperature, and ocean color. And so we now have a legacy of global essential climate variables from Earth observation satellites that is now going back at least 30 years. And it's thanks to these sorts of data series and time series data that we can start to understand our planet and how it's changing. And the most important one that we're going to be talking about a lot over the next few weeks with, for example, Dr. Anna Dogliati, Professor Arvind Singh, Dr. Rajeev Roy, Dr. Dionysius Ratsos, and Dr. John Gittings, is about ocean color and biogeochemistry. And we wouldn't be able to understand any of this without being able to observe our global chlorophyll budget from space. And if we look at the Earth for looking at ocean color and also land color, what we're seeing is productivity. It's the base of the marine food web, which is also really important for fisheries, which you're going to hear about from Dr. Cara Wilson, and water quality, which you're going to learn about from Dr. Milton Campbell. Primary productivity is another big one, and you're going to hear about that from Dr. Ryan van Meulen. Finally, primary productivity can tell us things about phytoplankton and these blooms and the way that they shift with seasons and respond to nutrients. This also tells us a lot about change, because what we're seeing here are fluxes. We're seeing seasonal pulses. We're seeing blooms, and we're seeing ocean deserts. So what we can learn from this is basically everything. We can learn about the marine food web, and we can understand as well how this might be affecting our climate, because the ocean is such a huge sink for carbon dioxide. And I know that Professor Jamie Shuttler is also going to be talking to you about how the ocean relates to the climate. So really, why wouldn't we measure ocean color? It tells us so much about everything, and there's very little that we can't learn from ocean color. So it's one of the really important essential climate variables that we can measure from space. Predominantly, we're interested in these guys, phytoplankton, microscopic single-cell drifting plants that are the base of the marine food web. And that's what we're looking at when we look at ocean color. We're looking at the pigment inside these microscopic organisms that are drifting in water. We're looking at the chlorophyll pigment inside the leaves of the plants and the stalks of the grass. And the fact that we can see that from space is just incredible. And you might not know this, but Trevor and Schuber are, in fact, the reason that I am a remote sensing scientist today. And it was the first time that they talked about the fact that we could measure phytoplankton in we could measure chlorophyll in a microscopic unicellular organism in the ocean from space. And Schubert talked about the power of collective action. And from that point on, I was hooked. So special mention to Trevor and Schubert for setting my life onto the track that made me a remote sensing scientist today. And we can also give special thanks to phytoplankton, not just for being the base of the marine food web and a very, very powerful carbon sink, but also for being so beautiful and inspirational. So phytoplankton transfer carbon from the atmosphere to the ocean. I won't go into this too much because I'm sure you're going to talk about it a lot in the next few weeks, but they are a really important part of the biological carbon pump and the base of the marine food web. Luckily, phytoplankton is really easy to measure because oceans are definitely not complex. There's definitely never sediment in the water. There's definitely never any CDOM in the water. It's never a problem to accurately measure chlorophyll. And if you're picking up sarcasm, that is correct. It's really, really hard sometimes to be able to unmix a signal that we see from satellite from a passive sensor, because phytoplankton and CDOM and suspended sediments, they are often mixed in the exciting coastal waters that we might want to measure. And so something that becomes really, really important if we want to measure ocean color, the things that we can control with the new generation of sensors, is the spatial resolution. So you'll see on the left over here, you can get very high spatial resolution from commercial satellites or aircraft or drones, but actually at 1 kilometer resolution, you're not losing a lot. You're able to see what is happening with those blooms. And Alchi, for example, gets data at 300 meter resolution. So that high spatial resolution is really, really important. But what is more important than the spatial resolution is often the position of the spectral bands and the spectral resolution, and specifically the sensitivity, so the signal to noise ratio of the instruments. And fortunately, that is something within our control. And Sentinel-3, which carries the ocean and land color instrument, I would say that this is really the cutting edge. It's a really nice continuity of MODIS and MERIS, which were American satellites, and it is helping us collect very, very good quality data of our oceans to get that ocean color data so that we can, as accurately as possible, derive chlorophyll concentration even in relatively complex waters. So that is the stuff that we can control. What is the stuff we can't control? Well, there are confounding factors. I'm calling them challenges, but I would say observing chlorophyll concentration in water from space is already quite challenging. So we can call these confounding factors. And the first is that Earth is cloudy. And what is the one thing that optical sensors can't do? They cannot see through cloud. There's very little we can do about that. We can't fix the sensors so that they can suddenly see through cloud. But there are other ways that we can address this confounding factor. So I just wanted to show you, this is a video of our Earth from December last year. You can see some storms developing, but you can also just see how cloudy the Earth is, and particularly over the oceans where we want to observe things like ocean color. This is a Sentinel-3 global data set of taken from Alchi of the Earth, only using Sentinel-3. Because remember, I said to you they act in they're working as a constellation to be able to give a daily revisit time. So one of the things that we are dealing with here is swath gaps and cloud gaps. If we combine Sentinel-3 A and B, which are operating together, we can fill in most of the swath gaps, but we're still dealing with a lot of cloud gaps. And this is where the moving to a level 3 product like the OCCCI, or even just doing merging, helps us fill in both the swath gaps and the cloud gaps. Because if I want to have a global ocean color image of the Earth, one thing I can do is I can look at the data that was collected today from Sentinel-3A and Sentinel-3B, and I can combine it with the data that was taken yesterday, because things in the ocean don't tend to change very, very quickly, especially in the open ocean. And so I can make a 2-day composite, fill in all of the swath gaps, but I've still got a lot of cloud gaps. The next thing I can do is potentially make a 3-day composite or a monthly composite or a seasonal composite in order to understand the thing that I'm interested in. If your application is, if you are unable to make these composites, you can still potentially always make 2 or 3-day composites to try and get rid of the cloud and see what is happening underneath. And you can also see how things haven't actually changed that much over the open ocean. You just have fewer cloud gaps. So these are the ways that you can address clouds, is to just get more and more coverage. There's another confounding factor, which is that Earth has seasons and latitudes. So depending where you are in the world, that has implications. I don't know if you've ever seen this image before. I think it's absolutely amazing. This was taken by a pinhole camera over a series of years. And this is in fact the sun. It's the path of the sun that the sun takes over a number of years. And for those of you who live at the higher latitudes, this may be more obvious than those of you that live closer to the equator. But if you're in the high latitudes, then where the sun rises at midday to is not above your head. It can be in your eye line, because of the way that the Earth is tilted. So we have these seasons and we have these latitudes. And that is a problem because of the way that light interacts with water. So I'll explain the problem of high solar zenith angle. So zenith is what happens when you imagine that you're in the middle of the Earth. So I want you all to close your eyes and please imagine that you're in the middle of the Earth. And then I want you to all look straight up. That is the zenith. So that is where the sun would be at midday if we didn't have the Earth on its axis and we didn't have seasons. Unfortunately, if you are in the high latitudes in winter, the sun does not conform to what I want, which is to be overhead at midday. It is often at an angle. And if that angle is higher than 70 degrees, then you have a high solar zenith angle. And that means that the light that is coming in is of poor quality and at an oblique angle. And the light also has further to travel through the atmosphere because of that angle. So by the time the light reaches the water, it is not entering the water as well. And so the outgoing light is also of a poorer quality. And if you want to look at things over an annual basis, if you aren't able to account for the solar zenith angle, you might be measuring something that you think is real, but it may be an artifact because of the quality of the light and the way that it interacts with the water when it is at a high solar zenith angle. So if you are doing your work in an area above that high solar zenith angle line at around 40 degrees north, you have to be careful of this effect during the winter seasons. If you are further north in Scotland, there is no light in the winter, and in fact, you can't do any ocean color studies at all. But this is also true for the southern hemisphere. If you are in Patagonia, you have no light, but if you are further south than even Cape Town, you're going to be struggling with solar zenith angles above 70 degrees, meaning you are going to have artifacts introduced into your annual data, and you need to be careful. You also have to deal with glint. So I know that India, for example, is on the line where there may be some struggles with glint, particularly when the southern hemisphere is experiencing winter. So that's also something to be aware of. The final challenge is that Earth has an atmosphere. Good for us, but particularly bad for remote sensing. And the oceans also have a surface. So we want to remove the radiance reflected from the sea surface and the radiance scattered by the atmosphere so that all we are left with is the water leaving radiance, which tells us something about the water that we're measuring. And we do that through an atmospheric correction. Now, if you're very lucky, you will never need to do an atmospheric correction in your whole life. But the way that you would do that is by working with level 2 data. And I think probably you're going to hear a lot more about this from Dr. Ben Loveday in the next couple of weeks, and potentially also Dr. Anna Windle. They're going to be talking about data access and data levels potentially. And I just wanted to give you a quick overview to say that if you work with level 1 data, you're working with data that's been very nicely mapped. And this is some of the different organizations will offer data where they have slightly different meanings for the different levels, but for the whole Copernicus program and for the Sentinel data, for optical data in particular, level 1 means that your data has been taken raw from the instrument and it's been converted into something you can use. It's been time-stamped, it's been mapped and gridded, but it hasn't had an atmospheric correction applied, and not much has been done beyond just providing you with the usable data. By level 2, you now have remote sensing reflectance, an atmospheric correction has been applied, and because EUMETSAT are super lovely, and other organizations do this as well, but particularly EUMETSAT, within the level 2 product, you have your geophysical variables. So you will have things like total suspended materials, you'll have chlorophyll A, and you can have different ways of deriving chlorophyll A as well. And you will have flags, which means you don't have to remember necessarily about solar zenith angle. All you need to do is remember to enable that flag so that you know where that is causing problems in your data, and glint is another flag that you can apply as well. So I would say level 2 data is absolutely the level I prefer working with, because so much value has been added to it, meaning that you don't have to spend so much time doing very technical work. There's also level 3 data, which I talked about the OCCCI earlier. If you do end up using OCCCI data over the next few weeks, or if you've used it before, it's a level 3 product because it has been merged in time. And so that is usually the indicator for a level 3 product. And at level 4, you've got gap filled, it's been interpolated, and perhaps a model has been applied. So when you work with Dr. Ryan van der Meulen on primary productivity, for example, from remote sensing perspective, primary productivity is a level 4 product that you can get, for example, from CMEMS. So I think that's about all I can tell you about ocean color, because there are so many more fabulous people and experts who are going to be teaching you all about it at a much higher level. But I hope that that has provided you with a nice foundation, so we're all on the same page. And I think it's time that we talk a little bit about sea surface height and why we measure it from space. So even though our oceans are essentially a continuous body of water, I don't know if you know this, the surface is not uniform across the planet, and sea levels will differ in space and time because of the geoids, so variation in Earth gravity, salinity and temperature, so the thermohaline circulation, for example, winds and atmospheric pressure at the ocean surface that can push and sort of pull water up against coastlines. There's tidal forces, and then there's currents. So all of these things serve to ensure that this continuous body of water is actually not uniform in sea surface height. So by the way, for the record, in case you wanted to know, this is my favorite map projection. It's the Spillhouse projection, and it unfolds the Earth so that we can just focus on the oceans. But what I wanted to show you was what I think is very cool, is that, for example, the North Atlantic is actually 14 centimeters higher than the sea surface of the Southern Atlantic. And the North Pacific is about 17 centimeters higher than the sea surface of the Southern Pacific. And the Pacific Ocean in general is 40 centimeters higher than the sea surface of the Atlantic Ocean. I don't know about you guys, I didn't know this until a few years ago, and I think it is extremely cool that we have such differences in sea surface height. But it also has implications for sea level rise and how different parts of the world will experience sea level rise. Because if you are living in an ocean like the Pacific and you have a low-lying island and that's your home, you are already dealing with a higher ocean, and sea level rise might impact you more than if, for example, you're living in the Southern Atlantic, where you have one of the lower oceans, lower sea surface heights. So we measure it as an essential climate variable because it helps us understand climate change and rising seas. It is a very good indicator of heat storage, and it helps us track things like eddies and currents. And we can only do this on global scales using satellite. And one of my favorite things to do is to look at eddies. I know eddies are scientifically very important, but I just think they look really beautiful in the satellite data. They tend to be mesoscale structures from 10 to hundreds of kilometers in size. They can transport different temperature and salinity pockets of water that even contain different types of phytoplankton across ocean basins. They're absolutely amazing, and they play a significant role in nutrient distribution. They can influence large-scale ocean circulation patterns, and they're really, really important in climate variability. So this is why sea surface height is one of those essential climate variables that we want to measure from space in order to understand marine ecosystem structure and function. So that just leaves sea surface temperature. Why do we measure sea surface temperature? Well, obviously it measures the weather, and I'm sure you'll hear more about this from Professor Jamie Shuttler. But I just wanted to show you this cool animation. This was taken from UmetView of a storm from last year. And you can see how along the storm tracks, these sorts of features tend to form anyway. They form over these warm oceans, and then they move towards, in this case, the east coast of the United States. But with warmer waters, there's more fuel for these types of storms. So the more fuel we have, the more likelihood we have of having much stronger hurricanes. It also means we're likely to have stronger winds because the frequency of rapid intensification events over warm waters is increasing because, and that causes higher winds within these storms, which already have incredibly high winds. The other problem is that they can hold more water because warmer air holds more moisture, leading to 10 to 20% higher rainfall in the more recent hurricanes. Plus, we have to deal with storm surge. If we have higher sea levels, like we've just discussed, then if we have storm impact and sea level rise, then we're also going to see a substantial increase in storm surge flooding, which we saw, for example, with Hurricane Sandy, famously actually putting New York underwater. So these are the things where sea surface temperature can also impact the weather and the climate. I'm sure you've heard of El Nino and La Nina. The way that we know we're in an El Nino or La Nina year is that we have very, very high quality sensors measuring sea surface temperature, and we can tell if there is a deviation of half a degree, and that allows us to discern whether we're entering an El Nino or a La Nina phase, which is really, really important for predicting a year's worth of flooding and fire risk on global scales. But ultimately, we also measure sea surface temperature because it is intimately connected with ocean biology. So it is a really key essential climate variable for marine ecosystem structure and function. Not only that, but it is relevant to our health. And I know you're going to hear a little bit more about this from Dr. Milton Campbell and is that right, for the human health? I might have left a name off there. I'm so sorry if I have. But human health is also linked to water quality, and sea surface temperature is an important part of that because it can also cause the increase in prevalence and risk of exposure to pathogenic species like Vibrio cholera. And you can measure ocean color and only ocean color for your whole career, or sea surface temperature or sea surface height, and you will have more than enough to do. But I would say that the really interesting stuff happens when you look at them together, because not only can you look at ocean color from a bloom perspective, but when you combine it with changes to, for example, things like sea surface temperature, then you might be able to understand the prevalence or intensity of new harmful algal blooms, or coral stress and bleaching, or aquaculture productivity. If you look at sea surface height and sea surface temperature together, you can find storm dynamics and thermocline depth changes, which has huge implications for productivity. Sea surface height together with ocean color, there we have the transport of phytoplankton blooms or pollutants within eddies, internal waves, and underwater volcanic eruptions as well. And so looking at these three things together really helps us understand our climate and the things that are changing on global scales, regional scales, and even local scales. So this is why I would say it is really important that we are able to observe our Earth using satellites. Fortunately, marine data are available across the Copernicus landscape. I'm not sure if you're going to see this map again during the next few lectures, I know it's really busy, but it is really important. And I want to show you that the traditional sort of marine remote sensing sits here under the purview of EUMETSAT and of course with NASA and NOAA, but these are the satellites that we are operating that are specifically for marine applications. However, ESA, the European Space Agency, which is responsible for the terrestrial component, it also carries and operates satellites that I think are really important for different types of marine applications. And I believe I have 10 minutes left, and I'm going to use those 10 minutes to tell you about slightly different ways that we can get marine data from the Copernicus system. So we've talked about Sentinel-3, our clever clogs over there carrying a mix of active and passive sensors, giving us ocean color, sea surface temperature, and sea surface height, because it is a dedicated marine mission. Now let's talk about Sentinel-1, our little bat of the series. It's a terrestrial mission with submarine applications, and it is an active sensor. It is only carrying one sensor, which is a synthetic aperture radar sensor, but it is giving us data at 10-meter spatial resolution. If we remember the highest resolution we were getting from Sentinel-3, it was 300-meter resolution. And if we think about the highest resolution data we can get from the geostationary satellites, that's 500-meter resolution. So 500 to 300 to 10. This is an incredible step change in spatial resolution. We have data going back to 2014, but these, because it's a terrestrial mission, the data are collected primarily over land and coastal waters. So it does have that terrestrial focus, but we do have coastal waters. And that gives us surface backscatter. So we can't see anything in the water, we can just see the water surface. So it is largely used for detection of things on the surface of the water. Vessel detection, for example, we can see really nicely in radar data. Oil spill detection, we can get the roughness of the water to give us wind and wave information. We can track icebergs in some of the cloudiest regions on Earth, and we can also measure inland and coastal flooding. Here is an example from Sentinel-1. Excuse me, this image is in VV polarization, which you don't need to remember, but what that means is the signal, because it's an active sensor, was sent out in the vertical polarization, and it was also received in the vertical, which gives us high energy and high intensity, so we can see a lot of surface roughness. And you can see how ruffled the water surface is here. You've got some in the corner here. It looks like you've got some internal waves, but you can see the roughness. And this makes sense because this image was taken outside of the Thames River estuary in January, which is winter. And so it's obviously quite stormy or windy. You can feel how unsettled the weather is in this image. But if you're not interested in that, and you're just interested in the development of the wind farms, then you can look at the polarization in the vertical and horizontal receiving. And that takes away that very intense surface backscatter. And instead, you can now focus on the very bright objects that are the wind farms and the boats. So they show up almost like stars against a black night sky. And that helps you look at a different thing. It's the exact same image from the same sensor. You're just looking at the data in a slightly different way. So this is what's magnificent about synthetic aperture radar at 10-meter resolution, is you can see individual boats and individual turbines within wind farms. Another example is a very big oil spill that happened off Karawang in West Java in 2019. If you look at the data again in the vertical, it allows you to see the oil spill. You're not actually seeing the oil spill. It's just that crude oil dampens capillary wave action on the water. So you're actually just seeing a lack of surface roughness, which I think is really cool. But if you're more interested in seeing the action of the boats that are trying to contain the spill, you can again just look at the same data in the VH polarization, the vertical horizontal polarization, in order to count the boats and see where they are aggregating. I hope you can see my mouse. If you can see these white spots on this background of the sea ice as it's forming, you can see the sea ice over here, and these bright white spots that look like they have shadows. these are in fact icebergs. So if you want to do iceberg tracking, these are very clearly identifiable within HH, which is the horizontal sending and the horizontal receiving, which allows you to see these icebergs in the Sentinel imagery. And this was taken off the West Antarctic Peninsula in 2023. I absolutely love looking at the HH data to see icebergs. What have I done with Sentinel-1 data? I've actually looked for sargassum invasions. So for those of you who don't know, it's a very invasive seaweed that started growing in the tropical North Atlantic in about 2011. It wasn't really there before. It escaped the Sargasso Sea, and it now lands up in the Gulf of Mexico and the Caribbean every summer. And it blooms in the same way that phytoplankton blooms. It's a macroalgae, and here you can see Barbados in 2018. The invasive sargassum that landed on its eastern shores was so bad that it actually caused Barbados to have to declare a state of emergency because the seaweed, once it starts to rot, also releases sulfurous compounds that put people in hospital when they breathed it in. So this is not just a case of some extra seaweed, it really is a very serious thing. And because these tropical areas are obviously often very cloudy, being able to see these seaweed invasions moving in from SAR is also very helpful. So there's a nice marine application as well for using the slightly unusual but high resolution data. It can also be used inland. I don't know, I'm pretty sure for those of you who've worked in India and live in India, you know about hyacinth invasions. This is an example of this is actually the Saigon River though in Vietnam, and you can see in this river, you can see these ropes in the middle of the river, and that's actually hyacinth that's moving down the river and clogging the river completely. We were interested in it because it transports pollutants and plastics, and we were interested in tracking how that changed the hydrodynamics of the river as well. So that's Sentinel-1. Sentinel-2 is another terrestrial mission with some marine applications. It's also operated by the European Space Agency, but the data goes back to 2015. It's passive, so it can't see through cloud. It's not the most amazing satellite for marine applications because it doesn't have as many bands as ALTRI. Remember, we need the spectral resolution, the spatial resolution, and the sensitivity. We don't really have that with Sentinel-2 in the same sort of electromagnetic spectrum range, where ALTRI has got 21 bands, Sentinel-2 only has 9, and at different spatial resolutions and at different widths, so not as sensitive. So you do get the spatial resolution, but you do lose that sensitivity. However, thanks to that high resolution, there is still a lot you can do. So this is an example of a bloom in the Baltic Sea in 2022. Can you see these lines through the bloom? These are the wakes of speedboats, and you can just see these incredible formations in the cyanobacteria bloom in the Baltic. But that high resolution, there's a little speedboat over there. It really allows you to see great detail. And over there, I don't know if you can see this, there's literally a boat that you can see is even red. I've not spotted that before, and there's a little cloud. So you can observe surface blooms, you can look at water quality. This was after a big storm in Florida in 2022. The wastewater that came out, these plumes were carrying extremely polluted water, and this overlapped with some marine sanctuaries, so it was really important to track where the pollutants were being dispersed, and we wouldn't have been able to do that even with such a good sensor like ALTRI. We needed the high spatial resolution to track those plumes. You can look at aquaculture. I'll give you a better example of this in a second. So this is off the Shandong province in China. This is a level 1 Sentinel-2 image, so no atmospheric correction has been applied. We will do an atmospheric correction though, if only it was always that easy. And this is a true color image. It's a visible image where we've combined blue, green, red bands of light to recreate what our eyes are used to seeing. But if I actually move into the near infrared, which looks at things floating on the surface of the water, you can actually see these aquaculture farms. And I don't know if you can see it in great detail on your screen, but it kind of looks like someone scribbled with a pencil down the line. And that is because it is actually picking up the individual ropes that are carrying the seaweed for these aquaculture farms. So again, you would be able to probably get some form of NDVI to look at at photosynthesis and productivity of the vegetation on these ropes, but more impressively, you can actually see the individual ropes themselves with this high resolution data. And because it's so high resolution, that does mean it's possible to also potentially get ocean color or the phytoplankton concentration in inland waters. And this is a very nice example of work that was done in India by colleagues at Plymouth Marine Laboratory, Stefan Simmis. And you can see the chlorophyll concentration of these rivers and lakes in the Musi River and the Hussein Sagar Lake. Okay. I'm going to very quickly speed through this. When it comes to use, now I've shown you a whole bunch of really cool data, and you have to, at the end of the day, decide which data is most appropriate for your project, because you're all doing very different things. And the rule of thumb is, unfortunately, it's very unlikely that you will be able to get everything. There's often a trade-off between temporal and spatial resolution. If you need data collected at a very specific time, you might be looking at drones. If you're happy with data collected every day, that's fine, but that means you're probably looking at data with a coarser spatial resolution of around 300 meters. If you need data every 2.5 minutes, you're going to be looking at data from geostationary satellites at 500 meter resolution. If you only need an image every few weeks, then you can probably go to the 10 meter resolution data. And if it's okay for you to just get one image a season, then really there's a lot that you can do. And I put this together. I know it's not very pretty, but I just wanted to show you where things sit, and there's very little overlap, and that's where decisions have to be made. So if you want data on a daily basis, that means that you probably have to be comfortable with 300 meter to 1 kilometer resolution, and these are your options from level 1 to level 2. If you're okay with getting data weekly and your priority is high spatial resolution, then you can get Sentinel-1 or 2 or Landsat. And again, if you're happy to get data every few minutes, you have to then be comfortable with spatial scales that are a bit coarser, and then you can get geostationary satellite data. So this is the difference between site scale, local scale, regional scale, and process scales. And again, this is where our level 3 and level 4 data sits if you only need something on a seasonal scale, but you can also get daily scale data at level 3 and 4. So I hope that that helps. And I'm going to end off now. I know it feels a bit abrupt, but like I said, trying to squash all of my enthusiasm into an hour was never going to be easy. But the things that I'd love for you to remember is that satellites are the best tool. If we want to observe the Earth, it really is the best tool in our toolbox for making measurements at meaningful temporal and spatial scales. Nothing is perfect. Trade-offs sometimes need to be made between temporal, spatial, and spectral resolutions, but the instruments themselves are incredible. They're cutting edge. They're the best that we have. And that means that we can at least make sure from the instrument and operational side that you are getting the best quality data possible. All sensors, whether passive or sensors, whether passive or active, whether in low Earth orbit or geostationary orbit, they all have their strengths and weaknesses and challenges, but ultimately they mainly have strengths. And despite any imperfections, satellites offer us incredible insight and understanding of processes, from marine to meteorological and from site-specific dynamics to global trends. And I cannot imagine a world where we can do marine ecosystem structure and functioning monitoring without satellites. So I'm going to leave you with something that is completely unrelated to anything unless you're interested in lightning. This is an instrument aboard the 3rd generation satellite at EUMETSAT. I just think it's really cool. It's our lightning sensor. It's the first time we've been able to look at lightning from space, and I just think it's quite a beautiful way to end the series. And I hope that you have enjoyed listening to me. I hope I've managed to enthuse you about why we use satellites to observe our Earth. Thank you so much for your attention.